Near black holes and neutron stars. Something impossible happens to time itself. It becomes a weapon against reality. These cosmic monsters create gravitational time dilation so extreme that minutes become years and eternity becomes a prison. Albert Einstein's most mind-bending prediction comes to life in these environments where gravity doesn't just pull on matter and energy, it pulls on time itself. Back in 1907, Einstein made a prediction so audacious it seemed like science fiction. He claimed that the stronger the gravitational field, the slower time moves. What started as a theoretical curiosity has become one of the most precisely tested phenomena in modern physics, with practical applications built into every GPS satellite orbiting Earth. This effect, gravitational time dilation, isn't just academic theory. It's correcting for time running 38 microseconds faster each day in space. Without these corrections, your navigation would be off by 10 kilometers after just 24 hours. But that's nothing compared to what happens when you venture near the universe's most extreme gravitational monsters like Sagittarius A, the supermassive black hole at the center of our galaxy. The first dramatic proof came in 1971 when physicists Hafele and Keating flew atomic clocks around the world on commercial airliners. Eastward clocks lost 59 nanoseconds, while westward clocks gained 273 nanoseconds, exactly matching Einstein's predictions. This was real verification that gravity affects time's flow. Let's start with something familiar: our own planet Earth. Even here, gravitational time dilation is measurable and real. If you placed a clock at the center of Earth and another at the surface, after 4.6 billion years of Earth's history, the core clock would be 2.5 years behind the surface clock. Earth's gravity is literally making time slower at its center. But this effect becomes dramatic when we scale up to neutron stars, one of the densest objects in the universe. These cosmic lighthouses pack the mass of our sun into a sphere just 20 kilometers across. Their surface gravity is so intense that it's over 100 billion times stronger than Earth's. If you could somehow stand on a neutron star's surface, every hour that passes for you would equal 65 minutes for someone watching from a safe distance in space. The physics behind this seems almost magical, but it's surprisingly straightforward. Einstein realized that acceleration and gravity are fundamentally the same thing through his equivalence principle. Imagine you're in an elevator accelerating upward. You feel pressed against the floor, experiencing what feels like increased gravity. Einstein's genius was recognizing this isn't just an analogy. Acceleration and gravitational fields are literally equivalent phenomena. This equivalence principle led Einstein to understand that gravity warps space-time itself according to general relativity. Think of space-time as a flexible sheet with massive objects creating deep wells. Time flows slower at the bottom of these wells, following what's mathematically described by the Schwarzschild metric. The more massive the object, the deeper the well, the slower time moves. The first laboratory confirmation came in 1959 with the Pound-Rebka experiment at Harvard. Robert Pound and Glenn Rebka Jr. shot gamma rays up a 22.5-meter tower and measured how gravity affected their frequency. Even across this tiny distance, they detected the predicted gravitational time dilation effect. Gravity was literally stretching time. But the most dramatic example happens near black holes like M87 Spleen, the first black hole ever photographed. These objects create gravitational fields strong enough to trap light itself. Near a black hole's event horizon, gravitational time dilation becomes extreme. If you positioned yourself just outside the point of no return, 1 year for you would equal 141 years for someone back on Earth. This is the real version of the famous twin paradox thought experiment. This isn't science fiction. It's the inspiration behind Christopher Nolan's Interstellar. When developing the film, Nolan insisted on realistic physics. The water planet where 1 hour equals 7 Earth years represented a time dilation factor of over 60,000 times. Kip Thorne, the Nobel Prize-winning physicist who consulted on the film, initially thought this was impossible. But after hours of calculations, he discovered it was marginally possible if the black hole was spinning near light speed. The reality of black hole time dilation creates mind-bending scenarios. From the perspective of someone falling into a black hole, they would cross the event horizon in finite proper time. But to an outside observer, that person would appear to slow down as they approached, their image becoming redder and dimmer until they seemed frozen in time forever. This is why black holes were once called frozen stars. The practical applications extend far beyond theoretical physics. Our global positioning system relies entirely on precise timing corrections for both general relativity and special relativity effects. GPS satellites orbit where Earth's gravity is weaker, making their clocks run about 45 microseconds per day faster. But they're also moving at high speeds, which makes their clocks run about 7 microseconds per day slower. The net effect is that GPS clocks gain 38 microseconds daily. This might seem insignificant, but at the speed of light, 38 microseconds allows signals to travel about 11 kilometers. Without correcting for relativistic effects, GPS would accumulate errors of 10 kilometers per day. Every time you use GPS, you're relying on Einstein's predictions about gravitational time dilation. The precision required is staggering. GPS satellite clocks are adjusted from 10.23 MHz down to 10.22999999543 MHz, a change of less than 1 part in a billion. This represents one of the longest-running tests of Einstein's theories, operating continuously for decades with perfect accuracy. Recent advances have pushed measurements to incredible extremes. In 2022, scientists at GILA achieved a breakthrough by measuring gravitational time dilation between atomic clocks separated by just 1 millimeter, about the width of a pencil tip. Even across this tiny distance, they could detect time flow differences due to Earth's gravity. Jun Ye, who led this experiment, describes it as entering a completely new ballgame, where quantum mechanics in curved spacetime can be explored. Their atomic clocks achieved precision of 1 part in 10 to the 20th power, meaning they could detect time differences equivalent to 1 second error over the age of the universe. This extreme precision opens possibilities for using atomic clocks as gravity sensors. Since gravitational time dilation depends on field strength, incredibly precise clocks can map variations in Earth's gravity. This could revolutionize monitoring groundwater, detecting underground resources, or predicting volcanic eruptions and earthquakes. Scientists are now exploring quantum time dilation. What happens when matter exists in quantum superposition while experiencing different gravitational fields? This could help us understand how gravity and quantum mechanics fit together, potentially solving one of physics' greatest mysteries. The implications extend beyond Earth. As humanity prepares to return to the Moon through NASA's Artemis program, gravitational time dilation becomes a practical concern. Due to the Moon's weaker gravity, clocks on the lunar surface run about 58.7 microseconds faster per day than Earth clocks. NASA is developing coordinated lunar time standard by 2026. The European Space Agency launched their ACES mission in April 2025, placing ultra-precise atomic clocks on the International Space Station. This experiment will test Einstein's theories with 50 times greater precision than ever achieved, comparing space-based clocks with ground networks to probe whether fundamental constants change over time. Looking toward the future, scientists propose networks of quantum-entangled atomic clocks to probe quantum mechanics in curved spacetime. These experiments could reveal new physics at the intersection of quantum mechanics and gravity, potentially pointing toward quantum gravity theory. The study also helps us understand violent cosmic events. When neutron stars collide, creating gravitational waves detected by LIGO and Virgo, extreme time dilation near these objects affects how we observe the collision. Gravitational wave detectors must account for these effects when analyzing signals from cosmic catastrophes billions of light years away. One profound implication involves the black hole information paradox. When matter falls into a black hole carrying quantum information, it appears frozen at the event horizon due to extreme time dilation. If the black hole eventually evaporates through Hawking radiation, what happens to that frozen information? Understanding gravitational time dilation is crucial to resolving this fundamental puzzle. Modern optical atomic clocks achieve such precision, they would lose less than 1 second over the entire age of the universe. These instruments can detect gravitational time dilation from raising them just 33 centimeters in Earth's field. This sensitivity opens applications like using clock networks as gravity sensors to monitor climate change by tracking ice sheet thickness and underground water reserves. The story represents one of science's greatest triumphs, transforming pure theoretical insight into practical technology affecting billions daily. From Einstein's 1907 thought experiment to today's quantum atomic clocks measuring time dilation across millimeters, this field demonstrates how fundamental physics becomes essential technology. Every GPS navigation, synchronized global communication, and precision scientific measurement depends on understanding gravitational time dilation. The same principles governing time near black holes ensure your phone knows where you are on Earth's surface. As we become a multiplanetary species, gravitational time dilation becomes increasingly important. Future Mars missions will need unprecedented timing precision across varying gravitational fields. The universe's most extreme objects serve as natural laboratories testing Einstein's theory's limits. We're approaching the point where we can use gravitational time dilation as a tool, rather than just studying it. Ultra-precise atomic clocks could become gravity sensors, dark matter detectors, or tools for discovering new physics beyond current understanding. From Einstein's theoretical prediction to today's quantum atomic clock networks spans over a century of human ingenuity. Yet we're still in early stages of understanding gravity-time interactions. Each experiment reveals deeper layers and opens doors to possibilities we're only beginning to imagine. From our planet's core to black hole edges, from GPS satellites to future lunar colonies, gravitational time dilation connects abstract theoretical physics to practical everyday applications. It reveals that time isn't just the backdrop for events, it's a dynamic participant in the cosmic drama, warping according to the gravitational symphony played by matter and energy across the universe. And perhaps the most unsettling truth is this: time was never meant to be the same everywhere. It only feels constant because our lives unfold in a narrow, gentle corner of the universe. Beyond that comfort, time stretches, thins, and bends under the weight of gravity, quietly abandoning the rules we thought were universal. Near the darkest objects in existence, time does not rush forward. It lingers. It slows to a whisper. A single moment there can drift past entire histories elsewhere. Not with violence, but with indifference. Civilizations rise, fall, and fade, while only seconds pass for those who venture too close. What's haunting is that nothing breaks when this happens. No alarms sound. Physics remains perfectly intact. Time does exactly what it is supposed to do. It follows gravity, obeys mass, and reshapes itself without concern for memory, attachment, or return. And yet the same fragile equations that allow time to freeze near a black hole are the ones guiding satellites above our heads, keeping our world synchronized, our maps aligned, our lives quietly on schedule. The universe does not separate the extraordinary from the ordinary. It treats them as one continuous story. In the end, gravitational time dilation reveals a humbling reality. Time is not a river carrying everything equally forward. It is a landscape, uneven and curved, where some paths move faster than others. And somewhere in that vast terrain, minutes can outweigh lifetimes, silence can last forever, and reality itself gently reminds us that we were never meant to fully grasp it, only to witness it.